Okay, we've got a worked example here for a work energy problem, a relatively straightforward one. This, I think, but one or two learning points in here. Let's have a look. A lawnmower of mass 9 kilograms is being pushed up a hill along the line of greatest slope. That means we're basically just this diagram we've got is just looking at the side, inclined at 15 degrees to the horizontal by a force of 80 newtons, acting at an angle of 60 degrees. That's coming through the lawnmower handle here. The frictional force is 15 newtons acting, opposing the motion of the lawnmower. So coming down here. Okay, so yeah, I've got our free body diagram, just drawing those two forces in basically. The resistance force here and the force coming in through the handle. I've not resolved this, but I think that's we can see what that's going to be. So the lawnmower is pushed 8 meters up the hill. Calculate first of all the work done against gravity, the work done against friction, and the work done by the force of 80 newtons pushing the lawnmower, and all those three leaders on to the second part B. So let's have a look. Right, okay. First thing we need to ascertain is the rise. This is the vertical height. So for 8 meters along here, how much are we going on? Well, of course, this height over the 8 meters equals sine 15. So the rise is basically 8 times sine 15. Now, the increase in potential energy that results from this force applied by the gardener is going to be the mass times g times the height. Okay, that's as per usual, 9 times 10 times 8 sine 15, and that works out to be 186.35 joules. So that is the work done against gravity. Now, the work done against friction, well, we are opposing this force of 15 newtons over that 8 meters. So that is simply the force times the distance. So that's 120 joules. That's the work done against the friction. And the part 3, the work done by the pusher, FP, basically that's the force resolved along the line of motion. So that's 80 cos 60 times the distance 8, which works out to be 320 joules. Okay. So those are the main things. So, what have we got? What we're not sort of kind of explored here is the kinetic energy. So we don't know the velocity. Let's have a look at part B. Given that the lawnmower was initially at rest at the bottom of the hill, find the speed of the lawnmower at the instant it has been pushed up 8 meters up the hill. So there's a sort of part 4 that we haven't done here, which is actually to find the increase in kinetic energy as we've gone up the hill. So let's have a look at this formula here. So the work that we do pushing. So where does that work go? What's it applied to? Well, it's applied to the increase in the kinetic energy. It's applied to the increase in potential energy, and it's applied to the work against friction. All these are in joules. We've got energy and work, but that's all in joules. So, well, the work done pushing we've calculated is going to be 320. The increase in kinetic energy, well, it starts from rest. The kinetic energy at the top of the 8 meters is basically going to be is going to be half mv squared. Well, half, what's the 2? That's the mass, kilograms, v squared. So that is the kinetic energy. This we've calculated before is the change in potential energy. And this is the work done against friction. So our 320 joules is basically used up by all these three things here. Okay, so that is just an equation in V, and V squared, and we can work that through, and that is just going to give us a velocity of 1.74 meters per second. So that will be the speed of the lawnmower at the instant that it's being pushed 8 meters up the hill. Okay, so that is it really. Those are our answers. I think just a kind of footnote, I guess, is that yeah, we start off from rest, we get to 8 meters. We don't know that the acceleration is constant here, I think, which is kind of one of the things that's you know, that is steering us towards a work energy solution here. So yeah, acceleration might not be constant. So had we been tempted to use Newton's law of motion or anything like that, then I think we might have not got very far. Okay, and I think just again, just perhaps recap on this statement here. You know, the total work applied is applied to these three things really. Changing the kinetic energy, changing the potential energy, and then opposing any forces. This work done is basically goes in heat or sound, or you know, or such things which kind of sort of they you know, it's not contributing to the mechanical energy, which is what these two items are. Okay, so good. Hope that has been useful. Thank you.